Hi, this is Mercedes.
And Carolyn.
And our structure is propyltoluene. First, we're going to analyze IR spectrum. Around 3000, we can see an aromatic ring, and a little bit to the right of that, we have an alkane. This area right here shows that our structure does not have any alkynes, alkenes, or oxygens. This area to the left of the aromatic ring shows that we don't have any amines present. And this area is not significant to our structure.
This is the mass spec for our molecule. This peak right here is the molecular ion peak. What this tells us is the molar mass of our molecule, which is 134. This peak here is called the base peak, and the difference between the base peak and the molecular ion peak is 29. What this fragmentation tells us is that there is a CH2-CH3 group in our molecule. In other words, we know now that there are 2 carbons and 5 hydrogens in our molecule. From our IR spectrum, we know there's an aromatic ring, and we can assume that this ring is a benzene ring, which means there are 6 other carbons. So subtracting the weights of the molecules from our molecular weight, this leaves 33 grams to account for in our molecule. And because we know from the IR that there's no other molecules besides carbon and hydrogen, a little algebra allows us to determine that the molecular formula is C10H14. This is the H NMR spectra for our structure. That there are 5 different signals tells us that there are 5 different types of hydrogen in our structure. We can tell that type A is for the aromatic ring because it's shifted farther down the graph. You can see that the CH2 at B and the CH3 at C have been shifted farther down the spectrum than they would be expected to. This happens because they're close to the aromatic ring, so they shift close to the aromatic ring. Now splitting is determined based on how many peaks are per each individual signal. So for A, for example, it's kind of hard to see, but you can count 1, 2, 3, 4 peaks at this signal. And we use this neat little equation where the number of peaks equals to the number of hydrogens on a neighboring carbon plus 1. So for A, where there's 4 peaks, on the neighboring carbon there will be 3 hydrogens, which you can see on this hydrogen, there are 3 hydrogens on the neighboring carbon. Another example of this is, for example, E. There's 3 peaks at this signal, and there are 2 hydrogens on the neighboring carbon, which is peaks plus 1. As for integration, the height of the individual signals depends on the number of hydrogens in that specific signal as well as their proximity to the aromatic ring. So for example, on A, there are 4 different types of hydrogens, so it makes sense that this line is longer than the ones with only 3 or 2 types of hydrogen. While C and E clearly have the same number of protons, the reason that C is taller than E is because of the shifting closer to the aromatic ring. That's what makes it a taller line.
Lastly, we are going to discuss the carbon NMR spectrum, which tells us how many carbons in the different types. There are 8 signals, which means that there are 8 different types of carbons. The first 4 signals that are shifted farther down the spectrum represent the carbons on the aromatic ring. Signals 5 and 6 are the CH2s, while signals 7 and 8 are the CH3s. For chemical shifting, the carbons on the aromatic ring do not stray too far from the expected values of roughly 120 to 160 ppm. The same goes for the carbons on the CH groups that range from roughly 10 to 40 when it should be around 5 to 55.